Okay. Hi everyone. Welcome to the stream. So today we're going to continue discussing 3D rotations for graphics and game engine development. Oh, hi Vernon. Thanks for joining the stream. So, as I was saying, today we're actually going to derive the 3D rotation formula, a general formula. I said that we're going to derive 3D rotation formula in general, but in fact, based on yesterday's knowledge, we can already do so for a particular kind of parameterization. So that is the Euler's angle. Okay, but that's not our focus today. We just want to mention that in passing. Perhaps we will do this another time. I'm just going to lay out the ideas. Remember, we gave the rotation matrices for the rotation was about each coordinate axis, x1, x2, x3. Okay, and here we have the description, the graphical description for the Euler's angles. Euler's angles, you have three angles, phi, theta, and psi. It turns out that if you just use consecutive transformations based on the rotations about these axes, you can just get the rotation matrices associated with given the Euler angles. So if you're given, that is to say, if you're given phi, theta, and psi, just use a bunch of matrix multiplication, you can get the rotation matrix for a rotation specified by Euler's angles. That's something we already can do. But this is not something we're interested in today. In particular, we're going to derive the Rodriguez formula. In Rodriguez formula, we specify the axis of rotation. We specify the axis of rotation n, and then we also specify the rotation angle theta. Okay, and the sign of theta, not the trig function sign, okay, but rather the positive or negative sign of theta is determined by the right-hand rule. The rotation formula is given as such, and we're going to derive it, and then recast the formula in quaternions. Okay, so once again, today's stream is going to be fairly quote-unquote computational, and it's not going to be very, so to say, theoretical. The whole purpose, good afternoon, hi. The whole purpose of what we've been doing so far is to develop computational facilities for describing rotations. Okay, so given these geometric characteristics, we hope we can implement it. Okay, or at least to be able to make sense out of the existing libraries. Because that's what we're trying to do. But yesterday somebody mentioned in chat that and asked whether I'm going to get to things like the Lie algebras and Lie groups. Of course, that's a very interesting topic, highly worth investigating. And so I thought about it, and later on I decided to have I'm not going to get into that today, but we're going to have a bonus episode, okay, a bonus stream on the main ideas of Lie algebra and Lie groups, purely from the point of view of 3D rotations. Of course, the Lie algebra and Lie groups are much more general. Okay, so of course, the idea is you can already see the many of the powerful results and the beauty of Lie theory purely from 3D rotation. And I believe 3D rotation was one of the principal motivators for Lie theory. And in particular, we're going to take a look at the so-called exponential map in Lie theory. And last but not least, the HCB formula, called the Hausdorff-Camber-Baker formula. So all derived elementary, using elementary means. Okay, so nothing You don't need topologies and nothing crazy. Okay, just use some matrix algebra. You can and also quaternion algebra, and you can see that. Okay, so which in my opinion is a good motivation to dive deeper into Lie theory, which is really a fascinating field. Okay, so without further ado, let's just get into the main derivation today, for which I'll have to start a new set of notes. Okay, so yeah, yesterday we did 2D rotations as well as a review of vector algebras in 3D. And today we're going to make extensive use of those knowledge. So, Rodriguez formula. This is, in my opinion, perhaps the most intuitive way to describe rotation. It's also, I mean, it's not perhaps the most computationally efficient, but you can at least get something done with this formula. Good afternoon. I'm from France. Well, thank you very much, Jean. So here, let's first draw the diagram. So suppose we have the rotation axis, and the axis is described, as mentioned, by a unit vector n. So suppose this is a unit vector n, and here we have a vector. So suppose we fix the origin at the starting point of n, and also the vector x starting from the same origin. Okay, and then we're going to rotate x about n by an angle of theta. And so after rotation, you get another vector like this. And our goal is to derive an expression for the new vector x prime in terms of the quantities, okay, this is awkward. Okay, here I just hate the position of this thing. Okay, so maybe I can move it around. Okay, so I would like to describe the new vector x prime in terms of the original vector x, n, and theta. So this is x. And be sure to respect the right-hand rule. This is theta. Okay. Okay. And the formula, I will just give it out as follows. So x prime is x times the cosine of theta plus n cross x times sine of theta plus n times n dot x times 1 minus cosine of theta. Okay, so let's take a look at the proof. And from the diagram, it is clear that it's perhaps a good idea to do a vector decomposition. So if we decompose x into two orthogonal directions, one in the direction of n, one that is perpendicular to n, the x perpendicular gets rotated, whereas x parallel is unchanged. So let's write it that way. So every vector x can be written this way. As x equals x parallel plus x perpendicular. So let's label those two components. So this is x parallel, the component of x that is in the direction of n. And here you have the perpendicular component, x perpendicular. It's perhaps a good idea to also draw the 2D view. Okay, so this is n, this is x, and we just orthogonally project x onto the n direction. This is x parallel, and this is x perpendicular. Okay. So of course we need to describe x parallel and x perpendicular in terms of the given quantities, and that's a nice exercise in linear algebra. So we can write x parallel as follows. So first of all, let's find the length of x parallel. The length of x parallel, of course, is just the length of x times the cosine of theta. I mean, not theta, but rather theta is the rotation angle. Let's just call this alpha, okay? Times cosine of alpha, where alpha is the angle between the original vector x and n. Okay. So that's the length. You also need the direction here, because this is a vector. We need the direction. Now the direction is just n, because n is a unit vector. If you multiply a length with a unit vector, it does not affect the length. Right? So yeah, that's it. So this is x parallel. Of course, we still need to express things like cosine of alpha, and this is where dot product comes in handy. So cosine of alpha, recall the definition of dot product. Let's put it on the side. So recall the definition of dot product. If you have two vectors, big A and big B, in R3, in fact, it can be Rn. The dot product of A and B is defined as the length of A times the length of B times cosine of theta, where theta is the angle between vector A and vector B. Okay, so here from this definition, the definition of the dot product, you can solve for cosine of alpha simply by considering the dot product between x and n. So let's do that. Cosine of alpha, of course, is just x dot with n over x norm or length times n norm. Okay. So we notice a few things. X length, first of all, cancels out, and n length is just 1. So therefore, x parallel has this expression that is x dot with n times n. Okay. So that's the parallel component. Of course, once you have the parallel component, the perpendicular component is really easy to obtain. It's simply x minus x parallel. So it's just x minus x dot with n times n. Okay. Of course, yeah, x parallel, as I was saying, x perpendicular lies in the plane perpendicular to n. Lies in the plane perpendicular to n. Okay, and we only need to understand the rotation of x perpendicular. Only need to rotate that, because x parallel remains constant. So next we need to describe the rotation in the perpendicular plane. That's our goal. So in that plane, you just get an ordinary 2D rotation. So how do we describe that? Well, let's notice something. We need to rotate, to do rotation of x perpendicular. So we want the rotation of x perpendicular. So why don't we draw a top-down view of this 3D diagram. So this is the circle in the 3D diagram, and here you have the original x perpendicular. So yeah, this is the original x perpendicular, and we wish to rotate it. This is a rotated version, so let's call it x prime perpendicular. So we want the x prime perpendicular. How do we get to that? And this angle of rotation is theta, that's given. Okay. And so we notice n cross x perpendicular is just x cross, it's just n cross x. Because you can write x perpendicular as x minus x parallel. And x parallel, as we know, is in the n direction. So n cross x parallel is 0, so you just get n cross x. So that's an observation. Okay. And of course, by the virtue of being a cross product, this cross product is also perpendicular to x. So furthermore, perpendicular to, hold on a second. Yeah, I'm trying to say is this cross product is perpendicular to x perpendicular. Because you see in this diagram, I'm looking at this triangle here. See, the focus is in this triangle. So x prime perpendicular has two orthogonal components as well. Then the component perpendicular, sorry, the component of x perpendicular prime in this direction, in the x perpendicular direction, is easy to obtain. The vertical, or this one needs a little bit of a thought. It's not so easy to obtain that because that's a job for the cross product. Okay, if that makes sense. We'll see why. We'll see why shortly. Okay. So this is why I'm considering the fact mentioned above. N cross m perpendicular equals n cross x. So furthermore, x perpendicular is perpendicular to n cross x, simply because n cross x is the outcome of the cross product. The cross product is perpendicular to both argument that takes the cross product. All right, so what else can we have here? What is n cross x? Remember, what is also note that the length of n cross x is what? The length of this vector, n cross x. The length of n cross x is, by definition, we mentioned, we defined cross product yesterday. That's the length of n times the length of x. Okay, and then times the sign of alpha. In this diagram, this is alpha. So this is x length times sine of alpha, which is exactly the length of x perpendicular. Here we used n has length of 1. N is a unit vector, so this is just the length of x perpendicular. Okay. So now the idea is we now have a expression for the length of this vector, x perpendicular. All right. So far we can write it as such. The rotated version of x perpendicular, which is x perpendicular prime. Okay, x perpendicular prime can be written from this diagram. It can be written as the x perpendicular times the cosine of theta. Hang on, so hold on a second. I'm trying to say is I need this part of the length. So I need this component. This component is, it's got the length of x perpendicular because it's on the same circle, and then times the cosine of theta, but it needs to be in the direction of x perpendicular. So let's create a unit vector in the direction of x perpendicular. So this x perpendicular over the length of x perpendicular, which of course just simplifies to x perpendicular times cosine of x. Okay, so yeah, this is the hypotenuse. Sorry, and that's not the hypotenuse, but rather what's that? What is this side called? I forgot. But one of the legs of the right triangle. Okay, and then times the unit vector in the direction of x perpendicular. And we also need the vertical component. So the vertical component is what? The vertical component is exactly n cross x times sine of theta. Let's see why. So the vertical component has length of, so first take a look at the length. The length is x perpendicular times the sine of theta. And we need a unit vector in that direction. Take a look at the diagram. What's the direction of n cross x? In the diagram, what's the direction of n cross x? Use the right-hand rule. N cross x goes this way. Yeah, so you see n cross x goes this way, so let me just put it here. Put it on the 2D plane. Okay, so this is n cross x. Perhaps in the 3D part as well. This is n cross x. So n cross x, as we mentioned, have the same length as x perpendicular. So we can substitute the length of x perpendicular to be, let me just, okay, let me add the unit vector component here. Okay. So we know that the perpendicular, this line segment, I don't know how to describe it, but basically that's the perpendicular component of x prime perpendicular relative to x perpendicular. I know it sounds a bit awful, but this is what it is. So that's the length, and then we need to multiply by the unit vector in that direction. And that vector can be expressed using the cross product. So that's why cross product is useful for describing rotation. So now you have just n cross x. Okay, so I'm sorry about the confusion of cross and x. Okay, so hopefully this does not go too badly. Let's just write x this way, okay, to avoid further confusion. I'll try to write x this way. Okay, and then divided by the x cross x, n cross x norm. But as we mentioned earlier, here, the x perpendicular length and n cross x length are the same. So it just simplifies to x perpendicular times cosine of theta, and then plus n cross x times the sine of theta. Because x perpendicular, since x perpendicular has the same length as n cross x. Okay, so perhaps I should emphasize that in the diagram to make the two vectors equal length. Okay, so perhaps this is better. It has the same length, right? N cross x and x perpendicular have the same length. So this is so far what we got. So now it's just a matter of substitution. It's just a matter of substitution. You add the parallel component and then you substitute, and that will be it. So now you add the parallel component, add x perpendicular. So the overall rotated vector x prime is x perpendicular plus x, x parallel plus x perpendicular prime. All right. Okay, so substitute the expression of x perpendicular prime, we get x parallel plus x perpendicular cosine of theta plus n cross x and then sine of theta times sine of theta. Okay, and now substitute. I'm just doing, now it's just a matter of substitution. So x perpendicular is x minus x parallel. So let's put that in. Okay. And you can expand this. Basically, we wish to collect x parallel, so you get x times cosine of theta plus x parallel 1 minus cosine of theta. And the last term remains unchanged for now. Okay. So, what else? Oh, the expression of x parallel is needed. The expression for x parallel we had earlier is just x dot n times n. So therefore is x cosine of theta plus the n cross x sine of theta, and then plus n times n dot x times 1 minus cosine of theta, because that's the expression of x parallel. So I think we have the Rodriguez formula fully ready. Yeah, you see, x times cosine of theta, that's the first term. N cross x times sine of theta, second term. And finally, n times n dot x, 1 minus cosine theta. There you go. Okay, so yeah, that's the Rodriguez formula now proved. So we wish to, at this point we managed to prove the Rodriguez formula, we wish to convert this into matrix forms, right? So we know rotation is a linear transformation, so x prime should be some matrix times x. So our idea is to recover the matrix form. Here you have vector, cross product, dot product, and all those stuff. So we still want r and theta such that the rotation matrix, still want the rotation matrix, say. So we wish to rewrite the above expression, the Rodriguez formula, in the form that x prime equals r and theta matrix multiply x. So this is what we want. So here we need to basically convert this into matrix form. The first term is easy. The first term, x cosine theta, is just a scalar multiple of theta. So we can write this as I times cosine of theta and then times x. So r and theta is 3 by 3. 3 by 3 matrix, all right? So here we need to introduce a topic that is we didn't have time to cover yesterday. That is, the cross product can be expressed as a matrix vector multiplication. So this is our interlude. That cross product can be written as matrix vector multiplication. Let's see how that's done. So recall, you got the coordinates formula. So let's say you have x cross y. Okay, x cross y, as we mentioned earlier, yesterday, you can use a mnemonic device and write that as a determinant. So E1, E2, E3 is the first row, X1, X2, X3 is the second, and Y1, Y2, Y3 is the last. And you expand the determinant. Simply, you get X2, Y3 minus X3, Y2, E1 plus X3, Y1 minus X1, Y3, E2. And finally, this is X1, Y2 minus X2, Y1, E3. Okay, and we're going to write this as a column vector. We're going to write it as a column vector. So in particular, we're going to keep things in a particular format. Okay. So the first entry, x2, y3 minus x3, y2, we're going to write it this way as minus x3, y2 plus x2, y3. You might be guessing, you might already guessed what I'm trying to do here. I'm trying to convert this as a linear transformation of y. So if we treat x as a fixed vector, x cross y is a linear transformation for y. Right? So for a linear transformation, it must have a matrix form. So that's why we're trying to find out the matrix for the cross product. So if we treat x as a fixed vector, x cross something, that operation is a linear transformation. So that's the first entry. I have no idea. John Conway is very formidable, right? Yeah. Hiroshi, thank you very much. Oh, I recognize your name. You're the guy who liked the British math book. I think, yeah, John Conway. I mean, I have some experience, but not full of his graduate complex analysis book. I quite like it. But go ahead and check it out. Probably is a good one. So, hi, Lockheed SR71 Blackbird. Yeah, I remember you liking British math books. So, for good reason. There are many great British texts. And actually, like my primary math language is English. So, yeah, so I guess I'm also biased towards the Anglo schools as well. Even though I try to appreciate other countries' math output too. So, yeah. Anyway. Hi, JC. Thanks for joining the stream. Okay, so let's write down the second component. So we got x3, y1. There's no y2 here, so we leave that as blank. Also, I'm finally catching the stream. Thank you very much. What time zone are you in? I don't usually do afternoon stream. Today is an exception, like yesterday. Okay, so that's the second entry. And the third entry is x1, y2. Okay, so x1, y2 here. And also minus x2, y1. So minus x2, y1. Locke really doesn't like vector algebra. Is that, have you ever read a Chinese math book? Yeah, I did. Is it really different? I don't think it's very different. I mean, perhaps it's a biased opinion, but I can't to put my finger on a particular Chinese style, okay, of writing mathematics. It's just, it takes me effort to translate the technical terms, for example. I mean, I learned the technical math terms in English, and I have to think, oh, what does this mean in Chinese, right? So it's very, of course, very different from everyday conversational Chinese. There are special languages for you for that sort of thing. Okay, so far my exposure to math literature are okay. All pretty much over 95% is translated English version, English or translated into English from French and Russian, other than the native English. So there you go. This is perfectly ready to convert this as matrix vector multiplication. So you get 0, y minus y2, minus x3, sorry, minus x3, x2 in the first row. So I'm trying to write this as a 3 by 3 matrix times the vector y1, y2, y3. So there's no mystery there, okay? It's just a simple exercise in first year linear algebra. We're rewriting the cross product as a matrix vector multiplication. We're not doing any sort of like representation theory. So this stream is very computational. Like the name suggests, this is for game engine and graphics engine development. So what we want is to get to the quaternion formalism. So practical users of this mathematical formalism can make sense out of the existing tools, or even better, code the algorithm themselves. Yeah, hopefully I can stay up here until the quaternion. Actually, very quickly, actually, we will get to quaternion very soon. So here we have x3, 0 minus x1. I will introduce quaternion in like, I think in 10 minutes or something like that. Minus x2 and x1, 0. Okay. So right now we're just trying to rewrite the Rodriguez formula as a matrix multiplication. Okay. So yeah. Therefore, x cross y is equivalent to, can write it this way as x bracket with a subscript cross times y, where the x bracket cross is x1, x2, x3. Sorry, that's nonsense. There's minus is 0 minus x3, x2, x3, 0 minus x1, minus x2, x1. Actually, I missed a subscript 1 here. And finally 0. What's so special about this matrix? Well, it's 3 by 3 skew symmetric. It's 3 by 3 skew symmetric. And in fact, every 3 by 3 skew symmetric matrix hides a vector. Yeah, I forgot a subscript in the middle. Yeah, I fixed that. Thank you, Christian, for pointing it out. Skew symmetric. Okay. So that's a nice way to represent the cross product. And remember, we also need something else. We also need to represent this product. N times n dot x. How can we write that as a matrix vector multiplication? So we managed to describe this part as a matrix multiplication. We still need this part. So this also takes a little bit of a trickery. So n dot with, sorry, not n, it's just n times the scalar n dot x. N dot x is a scalar. And we wish to write it as a matrix vector multiplication. How do we do that? Well, if you want to have, say, actually, you know what? Let's try to avoid trickery. Just do the brute force calculation. See what that lead to us. So n is just n1, n2, n3. Okay. There's no trickery here. Okay. You just need to expand everything using the coordinates formula and recognize, oh, this is actually equivalent to a matrix vector multiplication. So n dot x, of course, that's just n1 x1 plus n2 x2 plus n3 x3. Yeah, very nice. You guys, yeah, you guys were doing the fancy stuff like the Lie theory version, right? Exponential of this of the skew symmetric matrix gives you the Rodriguez. Right. Here I'm deliberately trying to avoid advanced machinery like matrix exponential and that sort of stuff. Okay, just the only prerequisite for this stream and yesterday were complex numbers and vector algebra. I'm not sure. Okay, I'm not sure. I'm not. I can't say if I'm going to make it as a dedicated series on quaternion. Perhaps later, I guess. Right now, I have too many things to finish up. Okay, I can't promise that. Sorry. So, yeah, because I'm not an algebraist, and I'm very much an applied person. So I learn pure mathematics on a need-to-know basis. Okay, so apologize if that comes as a disappointment. So if you have n1 n times n1, so just n1 squared x1 plus n1 n2 x2 plus n1 n3 x3, and then you have n2 n1 x1 plus n2 squared x2, and finally n2 n3 x3. Lastly, you have n3 n1 x1 plus n3 n2 x2, and finally n3 squared x3. Okay, yeah, and this is what? This is the matrix vector multiplication of this form. So it's n1 squared, n1 n2, n1 n3, n2 n1, n2 squared, n2 n3, and n3 n1, n3 n1, n3 n2, and n hold on a second, n3 squared, yeah, n3 squared, yes, and then times x1 x2 x3. Okay, but we recognize this is just n times n transpose. Just n times n transpose. So just in case that's still not clear, this is just n1, n2, n3. The column vector times the row vector n transpose. Actually, you know what? If I have done this from the beginning, this is already immediately obvious, right? So I think I overcomplicated things a little bit, or at least I chose a rather silly route. Okay, if I had just written down n dot x as simply n transpose x, then this would be done. So this is simply just n transpose times x. Okay. I wish to erase everything here, but I figured, you know what, I just leave my struggle here. It's a Gramian? I don't think it's a Gramian, no? This is the Kronecker product. Christian, I think if you talk about Gramian, we did see Gramian yesterday, right? When we, I'm not sure if you were here yesterday, but when we reviewed dot product yesterday, we covered Gramian. So basically, if you have a basis, E1, E2, E3, okay? E1, E2, E3 here doesn't have to be orthonormal. And if you just form the pairwise dot product, you get the Gramian. It looks similar, but here E1, E2, E3 are all vectors. But today N1, N2, N3 are the components of the same vector. So this is a Kronecker product. You can write it as N O times N transpose. This is also works. This is also called the outer product, I believe. Yeah, you can see the transpose right from the start. Gramian might be reserved for actual matrices. I'm pretty sure this is not a Gramian. So Gramian is like the metric tensor. So the entries of the Gramian are pairwise dot product. So you have a basis, and you take the pairwise dot product, you get the Gramians. Here, everything here is dot product, and while we have n1 times n1, that's just a scalar product. This is an outer product. This is or Kronecker product. I'm pretty sure they can't be the same thing. It always trips me that Kronecker product is a special case of tensor product, no? It's a concrete version. It satisfies the axioms of tensor product. So we're pretty much done here. So the Rodriguez formula here can now be rewritten in the matrix form. The first term is the easiest. It's just I times cosine of theta times x. The second term, as we argued, uses this special notation for the cross product. So this way you get, that's n bracket cross sine theta and then times x. Here you have, what's that? Here we have the n transpose, okay, n transpose 1 minus cosine of theta times x. Okay. So here, this is a matrix. You see, this is a matrix and this is a matrix. These are all matrices. Yeah, it's just a basic representation of tensor product, exactly. So there's a slight abuse of notation, but I don't think that's a big deal. It's like if you write every inner product not as curly bracket, but just x dot y, I think you're still fine. When we'll do a video on tensor for relativity. Well, perhaps not for relativity because I'm not an expert in that, but we will definitely see tensors in the information geometry stream. In fact, most of that stream will be on tensors, like classic tensor algebras. Because we're just going to, I keep mentioning that upcoming stream to tease that, but not because I really wanted to tease it, but simply because there are so many requests on geometry and I have to keep postponing it. Yeah. So on the information geometry stream, we will actually spend most of the time on tensor calculus, just classic tensor calculus, assuming nothing but just basic linear algebra. Okay, and we'll just take a look at the main ideas of information geometry and see uh, what's the payment, okay? What's the payoff of learning that subject, as well as what are the prerequisites? Because information geometry has a lot of prerequisites, and it's typically, as I said, I mean, as one of my professors said, one of my professors who does actual research on the topic, and says he says it's very difficult to find graduate student on this subject. Anyway, let's come back to this representation. Um, I saw applied mathematician like relativity. You see, well, not every applied mathematician is a mathematical physicist, right? Yeah. So, okay. Yeah. Let's try to simplify this. There's something we can do here. Notice, notice there's a particular. We have an identity. Okay. It's not completely obvious. General relativity has relatively few applications. Well, unless you work with GPS, I suppose, which I don't. So yeah, actually, here there's an identity, which I'm going to verify shortly. So you have the n transpose, n times n transpose equals the n cross product matrix squared plus I. So this is rather interesting. Let's verify that real quick. How do you find applications of already applied field? I guess you're talking about relativity that's theoretical physics, right? Or mathematical physics. All right. So let's verify this identity real quick. It's just a straightforward calculation. So here we have the n. Let's first calculate n cross product square. Once again, it is not a terribly creative process. It's just a brute force verification. Okay? But you should at least derive these formulas at least once if you are interested in using the Rodriguez formula. So there you go. You get minus n3 and minus n3 minus n2 n1 n3 n1 0. Okay. Okay. So multiply that by n3 0 and 1. Okay. So you get 0 times 0. This is minus, hold on. This is minus n3 squared minus n2 squared. 0, 0, n1, n3. This row times this column. Actually, n2 times n1 times n2 minus n1, n2. Okay. I haven't computed matrix multiplication by hand in a while, so hopefully I don't make too many mistakes. N minus n1, n3. Okay, that's good. Okay, and here second row, 0, 0, minus n1, n2. Cool. 0, actually minus n minus n3 squared, here, this row times this column, minus n3 squared minus n1 squared. Okay, cool. This row, that column, get just n. Did I make them? Hold on. Was there a mistake? Yeah, there's a mistake. Jeez. There should be a minus sign here. I messed up. I knew it. Okay, just double check. This is a cross product matrix. 2 minus in the upper block, in upper triangle region, and 1 minus in the lower triangle region. I might need to redo everything. Dang it. Yeah, sorry about that. It's just, I haven't done it by hand for a long time. Okay, so here you have this multiplication, that's minus n3 squared minus n2 squared. Second row, second column, 0, 0, minus n1, n2. Third column, minus n1, n3, n2, minus n3, n2. Okay. Actually, hold on. Minus n3, n1. A little bit annoying, but hopefully that's correct. Minus n1, n3. Yeah. All right. So let me just erase that. This here, second row, first column, 0, 0, minus n, actually plus 0, plus n1, n2. Second column, minus n3 squared. The n1 at the middle right of the second matrix. I think you're right. I just, sorry about that. I need to concentrate, okay? I'm not going to look at chat for the next, I mean, until I finish this algebra. Okay, this is embarrassing. This is, okay. My apologies for the carelessness. So minus n1. So now double check. Okay, so everything should be fine now. Times column minus n3 squared minus n2 squared. n1, n2. n1, n3. Okay. n1, n2 minus n3 squared minus n1 squared. n2, n3. Okay. Okay. Just a bunch of chores, but can still be a pain. 0, n1, n3. Okay. n1, n2, n3, yeah, n2, n3. And lastly, you get minus n1 squared minus n2 squared. All right. Okay, so just remove everything. So yeah, there we go. This is the square, and then plus I. So if we plus I, you're just going to add 1 on the diagonals, and everything else stays the same. So 1 minus n3 squared minus n2 squared. You see here, the fact that n is a unit vector comes into play, because the first entry is just n1 squared. So this is indeed n times n transpose. What a nice result. So the idea is you can write n times n transpose in terms of this cross product matrix. So that's nice. Okay, so there's no mystery going on whatsoever. It's just a brute force algebra. But I'm glad everything worked out. It just needs a little bit of a patience. Okay. So this is n times n transpose indeed. So that's proved. This is a proof. Okay, so now let's keep simplifying. Therefore, x transpose, so far, you get I cosine theta times x. Actually, we can factor x to the right. I cosine theta plus the n cross product matrix sine theta plus, and now that n times n transpose is expressed in this new identity. So you get I to n cross product matrix squared plus I times 1 minus cosine theta. Looks like we can do some simplification here. So that's the big matrix, rotation matrix. And now you can simplify I cosine theta seems to cancel here. So if you just get so you just get an I up front. I cosine theta gets canceled. That's an I plus n cross product sine theta, and then times the n cross product matrix squared. Why does it look like an open interval? No, I don't want that. So here, n cross product matrix squared times 1 minus cosine theta times x. So therefore, finally, we have the rotation matrix formula. Rn theta is just identity times the cross product sine of theta, and then plus the cross product matrix squared 1 minus cosine theta. So that's the second formula, which is of course completely equivalent to the Rodriguez formula, right? This is just a Rodriguez formula in the matrix form. Matrices are more than numbers in more than just numbers in a rectangle. It's kind of, yeah, I mean, there's no magic when you suddenly put numbers in a rectangle, because at the end of the day, these are just a shorthand for writing 3 linear equations in a compact form. As I was mentioning yesterday, so the reason we introduced this rotation matrix is just to save some writing. You don't want to write x1, x2 in each equation, so you just instead just write x1, x2 as a column and keep all the coefficients. Yeah. Right. And indeed, I mean, this is by no means a disparaging comment, because good notations are very important when it comes to suggesting new ideas. Think about dy dx, such a genius notation. So chain rule becomes obvious. I mean, not obvious, but that's the essence of chain rule, right? You get dy over du, du dx. Of course, there's a lot of controversy regarding that, but you can't deny the ingenuity when it comes to devising that notation alone. Right? So good notation is often, it pays down the road. Okay, anyway, so now we're done with the rotation matrix formula. So overall, now we've solved a big problem. When you're given a rotation axis and an angle, you can calculate rotation. So there you go. But now we wish to describe this in a more compact way. Remember, how many degrees of freedom are in rotation? I was talking about it yesterday. There's only 3 degrees of freedom in rotation. Let's think about it. Here you need an axis and an angle. The axis is a unit vector. The axis is a unit vector, so the 3 components of n has a constraint. So therefore, it's only 2 free variables in n. So total, you should have 3 free variables. Okay, and for that reason, mathematicians had been trying to compress this rotation matrix in a more compact representation. So you don't need 9 numbers. A 3 by 3 matrix has 9 numbers. Right? We saw yesterday that 2D rotation can be described just by an angle, and the complex number formalism perfectly encapsulates that, right? You just need e to the I theta, multiply by e to the I theta, and you get a 2D rotation. Beautiful. Right? So we wish to do something similar for 3D rotation. It turned out to be initially an excruciating task. Sir William Hamilton spent over, I think, a decade in vain trying to search for using 3D vectors to represent 3D rotation. If that makes sense, okay? Because we only need 3 parameters, right, to describe rotation. Can you somehow create a new kind of number? It's natural to think, oh, 2D rotation needs complex number. Complex number has 2 components, real and imaginary. So does that mean 3D rotation needs a 3-dimensional number to do that? And Hamilton tried this idea for years, if not decades, and failed. So perhaps you guys heard of the story that one day, like, he and his wife Helen went for a walk, and suddenly it came to him that he needs 4 numbers. So, and he carved down the rule needed on the bridge. The carving apparently is still there today, and hence quaternion was born. So the original motivation for introducing quaternion was very practical, is to simply encode 3D rotation in a compact form. Okay, just like how miraculously complex numbers encodes 2D rotation. So how does this work? Okay, so of course we're not going to go through the struggle that Hamilton went through. We're just going to present the result. Okay, if that sounds a little bit unmotivated, I'm sorry, because I'm not an algebraist. Okay, perhaps there is a natural way to lead to quaternion, but I'm just going to present the result and verify the quaternion rotation formula agrees with the matrix form or the Rodriguez formula. Okay, so there you go. Finally, we can get to quaternion. So quaternion works this way. once again, the introduction is going to be very practical. We're not going to discuss it from an axiomatic point of view. Okay, what properties characterizes a quaternion? But this is how it works. So here you have a quaternion is a number of this form, is an object of this form. Okay, and by the way, quaternion has this. The set of quaternion is denoted as H. Okay. Q is a quaternion. It has the form Q naught plus Q1I plus Q2J and plus Q3K. Yeah. So there's that. That's a quaternion. And you have this rule that the one that Hamilton carved onto the bridge, which is I squared equals J squared equals K squared equals IJK equals -1 with the rule. Okay, and we're going to use that to derive the formula for quaternion multiplication. And because quaternion multiplication is what encodes the 3D rotation. So to do 3D rotation, you need 4 numbers. Very counterintuitive. So addition is straightforward. Q naught plus Q1I plus Q2J plus Q3K, okay, plus another quaternion, which is P naught plus P1I plus P2J plus P3K. It's just component-wise addition. No mystery there. Okay, just like in complex number or in R4. Oh, by the way, QI's are all real. Okay? So it's just Q naught plus P naught plus Q1 plus P1. Yeah, you only need 3. I know. Technically, you're absolutely right. Lockheed SR, you're totally right. You only have 3 degrees of freedom. That doesn't change. That doesn't change. And because 3D rotation, you only need unit quaternions. You're completely right. You don't have 4 degrees of freedom suddenly. It's just it's so counterintuitive, right? You need 4 somehow 4 numbers gives efficient encoding. Okay. So the story of Hamilton is to let us know that if you struggle in math, this is completely normal. Everybody does, including geniuses. Hamilton was a prodigy. The guy William Hamilton was a prodigy. So if you struggle in your own math study, don't be discouraged. It's just the way it is, and it's glorious. Okay. So let's do the multiplication. You use this rule and see what we can get. Okay, Q naught plus Q1I plus Q2J plus Q3K. Multiply that. Just going to use that rule. Q-J. By the way, I put a link on geometric algebra if you guys are interested. There is a professor whose name is Alan McDonald. He makes videos on geometric algebra and also wrote books on geometric algebra. So go check them out. I'm not knowledgeable to comment on that, but basically, I think a lot of people are interested in geometric algebra and asked yesterday whether I'm going to cover it. Unfortunately, I will not because, I mean, I can learn it probably, but I just don't find it to be a good way to spend my time. Because one reason is that I find what what geometric algebra can do is already accomplishable by things like tensors and differential forms. I know that a lot of people might be disappointed, but I mean, I just don't have the time to study an extra area of math that seems already, you know, be pretty efficiently covered by something else. Perhaps you, I mean, I don't know if I'm ever going to do that, because the main interest of the channel is not really related to geometric algebra or algebra in general, actually. Yeah. So anyway, so here let's expand the product. So you get P naught, Q naught, Q naught, P naught. Okay, hopefully I don't try to focus. Okay, once again, I'm going to keep focusing on this expansion, and then I'll answer questions this way. It's less likely for me to make mistakes. Sorry about that. Q naught, P1. So it should be 16 terms. P1I plus Q naught, P2J plus Q naught, P3K. Okay, and then plus Q naught P1, sorry, Q1I P naught plus Q1 P1I squared plus Q1 P1IJ, and then plus Q1 P3 IK plus Q2 P naught I, Q2 P naught J, my bad, plus the Q1 P1 I squared, and plus Q2 P2 J. Jesus, I might have made a mistake here, huh? Q2J times P naught. Here, it's not I squared, but rather I times J. Q2J. Here, there's a mistake. Should be Q2 J times P1 IJ. Actually, JI, huh? I think the order is important here. The order is important. I might have messed that up. Okay, let me just double check, just to make sure there's no arbitrary change in order. Sometimes I change order randomly, which is not a good habit at all. So let's recheck. Q naught times P naught plus Q naught P1I plus Q naught P2J plus Q naught P3K. Okay, that looks okay. And then you can change the position of the scalar, namely the real number. That's no problem. Q1I times P naught, yeah. And then you get Q1 P1 I squared, that's okay. Q1 P2 IJ, that's okay. And Q1 P3 IK, that's good. Okay, finally here, Q2 J P naught, yeah, that's fine. Q2 J, Q2 P1 JI, yeah, that's nice. And then Q2 P2 J squared. Here you have Q2 P3 JK. Okay, and lastly you get, here, move the circle here. You want Q3 P naught K and then Q3 P1I, Q3 P2 Kj, and lastly Q3 P3 K squared. Okay, so that's the expansion, and now we need to figure out all these products between so-called imaginary units. Okay, so one thing we can notice is I square, j square, and k square are all -1. So that's nice. And there's also a linear term, or if you can call it that way, just I, j, k's alone. So these aren't any problem, but we need the cross product. Sorry, not the cross product, but the cross term. What's ij? Right? So what is ij? Well, from the last rule, ijk equals -1. Put it that way. Since ijk is -1, if we multiply k, you get ij squared, which is -k. And therefore, since k squared is -1, so you get minus ij equals -k. So ij is k. So ij is k. So this way you can figure out all the cross terms. Ij is k. But what about jk? What about say what about ji then? What about ji? So let's figure that out. Well, still, let's start from ijk equals -1. Let's multiply j on both sides. So jk is -j. Multiplying j on both sides. On the left. Okay. And then we just need ji. So to get that, we wanted to get rid of the jk. So ji jk squared is -jk. Is -jk. Okay. And k squared is -1. So you get j minus equals jk, so the minus sign cancels. Okay, and then multiply by j again. So j squared is jkj. J squared is minus, was that useful? Why did vectors actually, I'm not sure. Hold on a second. This seems unnecessarily complicated, right? I just need j. How do I get? Seems like. Oh, actually, you know what? Let's leave that for now. Jk should be readily obtainable. Jk should be readily obtainable. Here, ijk is -1. So left multiply by I squared jk is -I. So jk is just I. Jk is I. Okay. So we might need to find a table for that. Get a table for that. Okay, we'll summarize everything. jk is I. jk is I. Okay, and what about ik? So j is in the middle of this identity, ijk. J is in the middle. How do we get ik? Well, let's think about Okay. Well, I do code to answer your question. I do code, but I'm not a software engineer. If that makes sense. Um, so hold on a second. What is IK? What is IK? Basically, we need this table. We need a table to encode all the quaternion units, if you can call it that way. So we need a table, IJK, and gives us all the results. How do we get that? The diagonals are obviously all minus ones. Ij is k. We have that. But seem like we have trouble deriving ji, huh? Helpful thing to remember. Yeah, I'm trying to derive that, right? That's, you know, it's not much good thing if we just give that rule out of nothing. But because I mean, I'm trying to derive the anti-symmetry from these rules. Actually, I need a 1 here too. I need a 1 in the table too. To get the full table, you need a 1. So does that mean if you multiply j and 1, you get minus I as well? Is it always anti-symmetric? That's not right, right? I think the real numbers aren't affected. Okay, so here is just ijk. Well, we just derived that ij is k. Here, we derived ij is k, so that's fine. So what is ji? We can use associativity. Quaternion multiplication is still associative, so you have ij equals k. How do I get a ji? Well, let's try, put an I here, iji. You get ki. No? Ij is k. Use associativity. Here, hold on a second. I want to cook up a ji. What is ji? I want to derive that. Okay, ij times I, use associativity, is I times ji. The left hand side, this is ki. All right. But what is ki? We need ki. We need to derive ki. ijk is minus 1. Let's multiply I on the right. If I remember correctly, ki should be j, but I can't seem to derive. be able to derive it. Multiply ij and jk. Yeah, I know ki should be j. Is there a way to derive it? Sorry, guys. Let me take a look at the notes here. Perhaps, actually, you know what, guys? I posted a link in the stream on the papers. Perhaps they can help us out. Hold on. Hopefully I don't make the mistake yesterday. This way I don't, the sound is going to be weird, okay? The sound is going to be weird for a few minutes, but okay. Anyway, so hopefully I can figure this out. So there we go. So I put a few links in the stream, so now we can take a look at them. Yeah, so this one is a course notes in Stanford. So I was quite impressed by it, but let me just take a look. So here, addition and multiplication. So addition is trivial. The product of quaternions satisfies these fundamental rules introduced by Hamilton. Are these just introduced or can be derived? I was under the impression that you can derive these from the first formula. Can you? You see, addition of the two quaternions acts component-wise. Okay, the product of the two quaternions satisfies these fundamental laws introduced by Hamilton. So these are just rules, huh? I think they can be derived. But in the notes, it's just given. Yeah, it never really occurred to me because I was not very experienced when it comes to quaternion. But I was thinking, can we derive these from the first line? Okay. We say, of course, I mean, we just derived the first one, right? You just multiply k on both sides of the last equation and you get that. So how do you get the rest? How do you... So let's say, how can we derive, say, jk equals I? So from these, okay, so from these laws, I squared equals j squared equals k squared equals ijk equals minus 1. We've seen earlier that ij is k. Suppose now we need to show jk is I. How do we proceed? Yeah, the thing is, yeah, Lockheed, I completely agree, right? The first one should be fundamental and the rest should be able to be derived. So here, let me try that. Okay, here, I squared, suppose I squared is j squared equals k squared equals ijk equals minus 1. Okay. Then first you got ij equals k because ijk squared equals minus k, and you're done. Second, suppose let's try Hiroshi said ijk equals minus 1. Left multiply I, you get minus I. Ah, okay. Yeah, that's cool. Awesome. Thank you very much, Hiroshi. jk is I, and that's how you do it. Thank you very much, Hiroshi. So I squared jk is minus I, and you're done. Okay. Third, say we want ki equals j. How do you derive? Ki equals j? Ki should be j. So well, we can use the expression for k now, right? ki here, well, k is just ij, and then times I. Is that helpful? K is ij. But the thing is, we need ji, huh? We need ji, which we don't know yet. Multiply by j. You mean this? Hold on a second. So, well, Hiroshi is saying, if you derive, yeah, I mean, I haven't yet, right? So this is the first one, the second one, third one. Okay, so I'm starting from the left part. I want ki equals j. Can we do that? Ki equals j. Still, ijk equals minus 1. If we multiply I on both sides, so multiply I want ki, and ij is k, but I don't want it to use that, because this way ki gets destroyed. Multiply by ji. Let's try it. Ji, ij, ki equals minus ji, I. Yeah, Christian is saying multiply ji on both sides. So this way, well, I squared is minus 1, and the j squared is minus 1 too, so you just get ki. And on the right, yeah, that's j. Excellent. Excellent. Yeah, ji makes more sense. Thank you very much. So you know what? I'll put the credit here. So Hiroshi taught me the second one. And this one is due to Christian. Which man? Okay. Continue. So we have the left part, and now we need the anti-symmetry. So how do we get the anti-symmetry then? So we want ji. So ji should be minus k. Now the right side identity. Yeah, plug in the first two equations to the third. Good call. Yeah, good call. So now you have ji's individually. So ji is supposed to be ki. That's j. And I is jk. I is jk. So ij is k. It's just k cubed, which is minus k. And we're done. yes, this one credit is luminance. Thank you very much. Yeah, so now antisymmetry is shown, at least for the first one. Antisymmetry is now shown. Okay, so 5 says the here minus kj. I think you can use the strategy for the rest, right? Kj equals minus I is done the same way. So kj equals, so k is ij and j is ki. Right? K is ij, j is ki. So use associativity. The middle jk is just I, so just I cubed, so it's minus I. Right, so same idea. So the same credit goes to the same person. Okay, and finally, you got ik. Ik is minus j. Yeah, just now you have enough expression now. You can just plug in, right? Ik are I is jk, k is ij, and ki is j, so it's just j cubed equals minus j. I think now we have everything in the table. Okay, so yeah, this is the derivation for the multiplication table. Okay, the first one, if I may credit myself, okay, sorry guys, I'm pretty sure plenty of you figured that out as well. Okay. Okay, so here we have the table, the full table. This is very nice. You see, is there a geometric meaning for that? I'm pretty sure when we covered the 3D rotation in the quaternion formalism, we can interpret this geometrically. Just like you multiply I in a complex number is rotation by 90 degrees. So we should probably figure out, okay, what is rotation by I in the quaternion situation? Okay, so this is here, and we just put the table down. Ij is k, jk is I here, and ki is j. And then you just use antisymmetry. There's a minus k here, minus j here, and minus I here. So that's the multiplication table. Okay, and I'm going to remove the rest. Thank you so much for your help. Excellent. Yeah, so now we have this multiplication table, and we just do the substitution. Get the off-diagonal term, so this is minus j, minus k. Hold on a second. Did I miss something here? Q3 ki. I missed a k here. K missing here. K times I is j, which we just showed. And k times j is minus I, antisymmetry. Okay, so now it's we are ready to combine the terms into a quaternion. So the real part is q naught p naught minus, so all are all on the diagonal. So minus q1 p1 minus Q2P2 minus Q3P3. And you do notice this looks like a dot product. And in fact, this is what we're about to do. We're going to get the quaternion multiplication formula and then rewrite everything in terms of matrix, vector algebra identities, vector algebra notation. Right. Yeah, there's a geometric algebra reason for all of this, but you don't necessarily need to explain that. I mean, I can't explain because I'm ignorant. Okay, it's good to know there's a geometric algebra reason for this. Thank you for pointing that out. So yeah, and plus I times I. Let's look at the I terms. We have how many I terms? Well, first you got Q naught P1 and plus Q's I second, okay, I Q1 second row Q1 P naught. Third, got Q2 P3 and minus Q3 P2. Is that right? Yeah, looks okay. And then plus, you know what? We'll do the algebra ourselves and then check against the paper. How about that? J, you get Q0 P2, and then second row you get a minus. Should I put the minus at the end? Minus Q1 P3. Third row you get a Q2 P naught. And the last row you get a plus Q3 P1. So that's the third row. And the last row you get a K times Q0 P3, and plus Q1 Q2. Actually here, you know what? Let's put the minus sign, a negative sign first. Q2 P1, and here you got a Q1 P2. Q1 P2, and the last term should be Q3 P0. All right, so that's the quaternion multiplication formula. This is the multiplication in big H. Multiplication in quaternion. So yeah, you see here, you can notice there's some odd business going on. You have it's very much reminiscent to some of the matrix vector multiplication formula. So so there's so many patterns going on, so many patterns. It's perhaps a good idea for us to reorganize things a little bit. So let's just give things some names. Let's just give things some names. So names, we have, just like in real, just like in a complex number, you have real and imaginary parts. We call Q naught, so Q equals Q naught plus I Q1 plus I Q2, JQ2, and K Q3. So Q naught is called the scalar part. The scalar part of the quaternion, and the rest is called the vector part. And we write S of Q, the scalar of Q, to be Q naught, and the vector part of Q as big V of Q equals I Q1 plus J Q2 plus K Q3. So that's the vector part. And just like in a complex number, you can define conjugate. names. Okay, this is a conjugate. So Q bar is Q naught minus I Q1. Exactly the same like in complex conjugate. J Q2 plus K minus KQ3. Minus KQ3. So, and also you have the square norm, or the absolute value. So the square norm, as you can probably imagine, this is just like the Euclidean norm in R4. Squared Euclidean norm in R4. Okay, and we can verify that this is just like in complex number is Q times Q bar. So verify. The square norm equals Q times Q bar. It's good exercise. So let's multiply Q and Q bar. So what happened when you multiply Q and Q bar? Use the big formula. So everything, no P, okay, everything just Q now. And we want to see if there's any cancellation going on. Probably there is. Remember how Q bar is defined. Q bar keeps the scalar part and flips the sign of the vector part. It's going to be a long verification. I mean, that's okay. We're doing this for the first time. Okay, so here, just want to verify the cancellation. I mean, what's the point if I just lift all these properties and then move on? Like, you can read a book from that. Right? So as I keep saying like this. So even like nobody is watching the stream, if I'm learning this stuff myself, I would do exactly the same thing. And now I just need to do the talking as well. So really, for me, there's no difference. Okay, so if I just say, okay, these are properties, you can verify them. Like, why would I even do the stream? You can't read it from a book. Okay. So the whole point is to go through this process. The good thing is you only need to do this once. That's it. Once you've seen it yourself, then you can move on and do more interesting stuff. Okay, so there you go. In Cayley-Dixon construction, a quaternion is a C2 vector space. Yes, I heard that. Yes, I think I didn't know the name, but I seen that construction of complex number. Sorry, not complex, but quaternion before. It's like pairs of complex number. Okay, but I mean, in this one, in this stream, I'm just going to keep things computational. Okay, I'm not going to be terribly deep when it comes to the algebra stuff. All right, so here we have, how do we, well, now you see things, how do things cancel out? Because Q naught, which I just erased, is just minus P naught. Sorry, it's just, sorry, that's not good. That's not what I mean. P1 is minus here. This is minus P minus Q1. And P naught is just Q naught. So they cancel out. Okay, and Q3, P3, Q2, P3, Q2, P3, P3 is minus Q3. And P2 is minus Q2. So we can clearly see I disappears. Personally, being too computational hides the geometry. Yeah, we're getting to the geometry, right? It's like when you define complex numbers, I mean, the verification is shorter, but first you define the complex multiplication just using these abstract rules, and then you suddenly realize, oh, these are actually 2D rotation. It's just that we're not going to hide the geometry. Okay, it's just that at this certain early stage, the algebra needs to check out before moving to visualization. So P2 here is minus Q2. Because let's be honest, I mean, quaternion isn't the most intuitive thing in the world, at least for beginners concerned. So hold on a second. Why do things not canceling out? So Q2, did I make a mistake there in the formula? So I wrote Q0 times P2, and P2 gets swapped to minus Q2, and Q2 and Q2P0. Q2P0. P0 is minus P0. Each IJK rotated independent. Okay. Anyway, yeah, that's the reason, right? We'll get into the rotation soon. So here, actually, what's going on? Here we have Q. I have Q0P2 times Q2P0. P0 is minus Q0. So why do they not cancel? Q0P2 becomes Q0 minus Q2 plus Q2 P0 is minus Q0. They don't cancel. Instead, after the fact, yeah. See, that's why I strongly promote the algebra suite. Okay, okay, okay. Here, so why? Yeah, I get you, Lockheed. I'm just trying to. Okay, did I make a mistake in the algebra formula? You know what? Let me take a look at the paper. The paper says the paper does that's not very nice. Oh. Okay. Is that the same as the one I got? Is that the same? So the real part, this is the real part. Yeah, that's the real part. So here it actually grouped into this nice vector form. Let's try to verify that. So P naught times Q1 P naught. Okay, yeah. So P naught times quantity Q1I plus Q2J plus Q3K is this column here. And Q naught times P1, P2, P3K is this column here. So we're good. Okay, finally you got P, hold on a second. This is wrong. This is wrong. This is not consistent with the formula. Oh, actually, I put Q before P, no? Yeah, I put Q before P, so this is fine. This is fine. This is fine. And fine, yeah, this is fine. So, yeah, it's indeed the same as what's in the paper. Question: your formula is right. The substitution for Q bar is where you messed up. Yeah. I suspect the same thing. So here, where did I substitute wrong? So here, it should be Q naught times minus P bar. Oh, actually, yeah. So P naught does not change. Yeah, P naught does not change exactly. So P naught, the scalar part is unchanged. So that's why. So yeah, that's why. So here, it still should be P naught. It does not change. That's where I made a mistake. Okay, cool. So now everything should be fine now. So here, continue. If we write Q3 times minus Q1, yeah, this is minus Q1, and P3 is minus Q3, yeah. Okay, yeah, it never occurred to me that because P naught should, is the same after taking conjugate. So yeah, this should be minus Q3. Excellent. So everything here cancels too. And finally, the K formula. In the K term, you get Q naught P3. P3 is minus Q3. Minus Q3. And once again, let's not make the same mistake. P naught does not change. And here P2 is minus Q2. Substitute P2 equals minus Q2. And finally, P1 is minus Q1. And we're done. What are you guys doing? I'm trying to verify properties of the quaternion. Right? So remember, today our goal is to introduce two formalisms for 3D rotation. We did one already, which is 3D rotation matrix, aka the Rodriguez formula. And now we're getting into quaternion. So now we're still in the basics of quaternion algebra, just to familiarize ourselves with the rules of quaternion. So quaternions multiplying quaternion, exactly. So Aaron, so that's what we're trying to do. We haven't introduced the quaternion formalism yet, just trying to get a feeling of how the multiplication works. Because eventually, the quaternion multiplication is what will give us 3D rotations. Okay. So there's that. All right. So this indeed tells us this is Q naught squared plus Q1 squared plus Q2 squared plus Q3 squared. That's the square norm of Q. There you go. Okay, so that's cool. That's verification done. And once you have that, just like in complex numbers, you can use this identity to construct the expression for the inverse. So if Q norm is non-zero, then you can write Q inverse, the multiplicative inverse of Q, as you can write it this way: 1 over Q, and you multiply Q bar on top and bottom, so it's Q bar over Q bar. Q times Q bar is, so I guess this is the only situation where you have commutativity, right? Perhaps not the only one, but one instance you have commutativity. You can swap Q bar and Q and get the same answer. They're just Q quantity squared. In general, quaternion multiplication is not commutative, which shouldn't be, because 3D rotations aren't commutative. If it is commutative, then we're in trouble. So yeah, so that's the formula for the reciprocal. Okay. All right, so that's cool. And let's use the vector form. Like we have the vector formalism now. You can consider a quaternion as a vector, a scalar vector form. So here, therefore, we're going to identify Q naught plus Q1I plus Q2J plus Q3K as a scalar vector pair. The scalar is Q naught and the vector is V. Okay, where V is, of course, Q1I, Q2J, and Q3K. So that's the vector part. And now let's do all the algebras in terms of the scalar vector pair, right? This is a scalar vector pair. So see how that works. So first, addition is easy. You get Q naught U plus, say, P naught V is just Q naught plus P naught U plus V. Okay. So at this early stage, might as well put the vector sign on to avoid confusion. Okay, this is addition. Multiplication, as we already seen in the paper, is a little bit trickier, but it's not too hard to spot what's going on. So let's write the multiplication formula. I left space here, did I? Okay, I didn't do much, but there's a reason I left space here because we wanted to see this can actually be organized in a very nice way. Never thought about the scalar vector pair perspective. Yeah, it's in the paper, so that's why that's how I knew about it. So there you go. Here we have the you see the this looks like, okay, so first of all, this looks like here let's write just P1 Q naught Q naught P naught minus Q1 P1 plus Q2 P2 plus Q3 P3 quantity. Okay, that's the first row. And then we can look at the terms here. So you see, if you got a negative sign, for the term that got negative sign, you can construct sort of a cross product. This is sort of like a cross product. So I'm grouping terms like Q1, P1, Q2, P2, and Q3, P3 to cook up a dot product. And here you have a perfect structure for cross product. So let's write that down. So you got I times Q2, P3 minus Q3, P2 plus J Q3, P1 minus Q1, P3 and K Q1, Q2, Q1, P2 minus Q2, P1. And what about the rest? Well, look at here. You can take out the Q naught. So the Q naught times P1I plus P2J and finally plus P3K. And lastly, you get P naught times Q1I plus Q2J plus Q3K. Yeah, so that's the alternative form for multiplication, completely equivalent to what we just derived earlier, but it has a nice vector interpretation to it, right? So here, the first row, you can see this is just a Q naught P naught minus a U dot V. That's the scalar part. And then you got the second row here is just a U cross V, cross product, and then just plus Q naught times the vector part of P, which is U, and then P naught times the vector part of oh no, this should be Q naught times V. My bad. And finally P naught times U. So that's the vector formalism. Right. So there you go. So that's the not complex but quaternion multiplication in terms of scalar vector pair. Put it here. Okay. Q naught U times P naught V. Okay. This would be Q naught P naught minus U dot V. Okay. And then plus, actually no, not plus, but this is the scalar part, right? So everything else should be in the vector parts. Okay, so the vector part, as we mentioned, have Q naught V plus P naught U and plus U cross V. So the cross product appears here. This multiplication. So conjugate is easy. Q naught U taking conjugate is just Q naught minus U. Okay, that's conjugate. And square norm. So the square norm of Q naught U is just Q naught squared plus the square norm of U squared. Square norm of U, okay? That's it. And finally, you got the reciprocal. So here, the reciprocal, say, if you want to take the inverse of Q naught U, okay, the denominator is Q norm squared, which we just derived. That's Q naught squared plus U length squared. And then put a conjugate on top. So conjugate is just Q naught minus U, as mentioned. So there you go. So these are the formulas in vector form. In my words, put them together. Okay, this is our formula sheet, little cheat sheet for quaternion algebra. So with all of those things, you can do the usual addition, subtraction, multiplication, and division. Algebra in H. Okay. So let's look at a special case. That's so-called pure quaternion. So pure quaternion is like purely imaginary number where you have a zero real part. Here you just have a zero scalar part. So for so-called pure quaternions, let's, for example, consider what's 0u times 0v. Substitute P naught Q naught equals 0. You just get minus the dot product of u and v and the cross product. Is that like geometric algebra? Does like geometric algebra put cross product and dot product together? I'm not sure. Okay, I might be talking nonsense. Okay, so this is pure quaternion. You have this nice little reduction here. All right. So now finally we are ready to discuss rotation. We're finally ready to discuss rotation in the quaternion form. So this is very exciting. So how do we express? Well, the starting point is still the Rodriguez formula. We're going to give the formula here. Ming discovered geometric product. No, I mean, I think I watched a video or two, and yeah, I sort of vaguely remember the geometric product has this dot product with a cross product together. Like, okay. Anyway, so yeah, yes, the definition of geometric product is typically the sum of the interior product and the exterior product. Yeah, fair enough. Okay. So there you go. So we're still doing the same thing, okay? Encode the rotation encoding, just rotating in 3D, given an axis and an angle. Sorry. How do you do that? Rotation is described by n and theta. And the formula is nothing short of pure magic. So Q is cosine of theta over 2. And n, that's the vector part. So cosine of half theta, that's the scalar part. And n times the sine of half theta is the vector part. So this is what encodes rotation. Okay, so how on earth does this even work? It works this way. So here, we can, to represent this as rotation, we're going to identify the 3D vector as a pure quaternion. It's not pure magic, actually. It's probably not, right? It's just that, you know, I always bring up this story by Andrew Wiles. When you learn a new area of math, it's like entering a dark room, and you keep stumbling upon furnitures, right? Knocking things over and falling over and that sort of stuff. And one day you figure out the location of the switch, and you turn the switch on. Suddenly, you know you literally see the pieces of furniture. So I'm currently in that dark room now. Okay, it feels pure magic to me. I know it's not, but you know, math is not sorcery, right? It's just a matter of experience. So we're going to identify. I put up these notes, so identify, but after you show you why it would look natural. Exactly. So we're going to do some numerical examples today. Okay, don't worry. So here, we're going to identify the vector x, which is x1, x2, x3, as a pure quaternion, as big X, which is 0, that's the scalar part, and x is the vector part. Which is basically saying 0 plus x1i plus x2j plus x3k. Okay, and by the way, q is if we write it as the usual notation for quaternion, this is just cosine of half theta over 2 plus n1 sine theta over 2I, n2 sine half theta j, plus n3 sine half theta k. So that's it. Not sure what intuition the notes you're using provide. So no, it's like my own notes. I read the Wikipedia and I put down the formulas. Okay, it's not like a piece of like a paper. Okay, it's like my own notes and I put it down on written on a piece of paper. Okay, so okay. Anyway, actually, I don't know a good reference on the like introducing quaternions naturally. I don't know a reference on that. Okay, it would be great if somebody point to a good reference. Please let me know. But here, right now, I did this definition, and here comes the formula. Okay, the resulting quaternion rotation is this. So rotation is x prime equals q times big X and q inverse, the reciprocal. So that's the formula. So that's the formula, okay? And now we're just going to verify this actually agrees with the Rodriguez formula. So we need to verify need to show the x prime is 0 and r and theta times x, basically. You like matrix book for undergraduates. Thank you very much. Yeah. A lot of people are very, a lot of people in this community are actually very knowledgeable in algebra. Thank you very much. I was very lucky. So I don't know actually why, because I never posted any algebra content on the channel. Simply because I have nothing good to say. It's like my algebra is very rudimentary. I only taken like linear algebra. But a lot of people on the channel, I mean, in the community of this channel, are very knowledgeable in algebra. So I'm very lucky. And by the way, here, because of Q is unit, Q is a unit quaternion. First of all, first note that Q is a unit quaternion. So Q squared is Q norm squared is cosine squared over 2 plus n norm squared sine squared theta over 2. Of course, this is just 1, since n norm squared is 1, so this is 1. And Q is unit, and this immediately tells us that the reciprocal, according to the formula, is just Q bar, because the denominator is 1. So that's nice. So Q bar is very easily obtained. You just need to reverse the sign of the vector part, and you're done. So this is extremely computationally efficient. Perhaps one of the reasons that quaternion is so popular in game engine development. I represent the axis of rotation in this formula, which you only have single axis for 2D rotation, so you only have I. You can represent complex number rotation in a similar format. Yeah. So that's a very good perspective, Lockheed. So here we have this formula. Now we're just going to do some, once again, this very mechanical verification. I'm just going to compute, and it turns out to be actually the same as the Rodriguez formula. So let's try to do that. Just to simplify notation, actually, I'm going to write, actually, you know what, I'm not going to bother. I was going to be lazy and write cosine as C and sine as S, but anyway, let's just verify that. Okay, so derive Rodriguez formula. From quaternion multiplication. So basically, we just evaluate, compute, just a straightforward computation, right? So this sort of proof really is not terribly interesting, but it's because of the heavy price was paid in discovering the right definition. Once the right definition is discovered, the proof is a trivial matter. It's just a computation. Okay, there's no ingenuity involved. Right. So a pure mathematician, for pure mathematician, a lot of the hard work went into the trials and errors of good definitions. Quaternions are not a field like algebra because because the commutativity fails as it should be. I was just saying that pure mathematicians spend a lot of time refining their definitions to make the proofs easier. This is a lot similar to applied mathematicians have to test different problem formalism and modeling assumptions. Because a lot of the actual hard part went into set up the problem. So there you go. Okay, so Q, as we mentioned, let's just calculate what is Qx. Okay. Qx, as we mentioned, is cosine of half theta. Cosine of half theta, sine of half theta, n, and x is 0, big X. Big X is 0, vector x. Okay, put a vector here. Let's use the formula. So the real part, or the scalar part is so cosine half theta times 0 minus the dot product. So dot product gives you sine of half theta and dot product with x. So that's the scalar part. And the vector part would be, think about that. So it would be cosine half theta times x plus sine half theta n times 0, and finally you got a cross product. So you get sine half theta times n cross x. So that's just a multiplication formula, which we just mentioned. And also generalization connection, yeah. So indeed. Here, so to simplify, you just get rid of the 0, so you get minus sine half theta n dot with x. There you go. All right, and then you have cosine of half theta times x plus the sine of half theta n cross x. Nice. Okay. And now we need to multiply by, you cannot simplify this further, so we're just going to multiply that by Q inverse. So Qx times Q inverse Right, so put this result here. And Q inverse, as we mentioned, is just Q bar. Unit quaternion. Taking inverse is just the conjugate. Nice. All right, so the scalar part would be minus sine theta over 2 cosine of half theta, and then do a dot product of the vector part. So you minus subtract by cosine half theta x plus sine half theta n cross x, quantity dot with n, dot with minus n, so dot with minus n sine half theta. So that's the scalar part. That's the scalar part. And now do the vector part. So it's going to be a little bit complicated, but it's fairly mechanical. All right. So the first scalar minus sine theta 2, theta was, hold on a second. Oh, I missed something. I missed the dot product. That's not good. By the way, this scalar should be 0. This scalar should be 0. So the real part, or the scalar part, should be 0. N dot with x. All right? Okay, and the vector part is sine half theta n dot x times the second vector, which is minus n sine half theta plus second scalar, which is cosine half theta, times the second vector, which is cosine half theta, x plus sine sine of theta over 2 n cross x. It's a drudgery, I know. And lastly, you got the, hold on. Lastly, you got the plus the cross product term. So you need the cosine half theta x plus sine of theta over 2 n cross x. This thing to cross negative n sine half theta. All right, so that's it. That's it, right? So anyway, thank you very much, Lockheed. Have fun. Have a nice sleep. Thank you very much for joining the stream, and thank you for your comments. Those are great. Okay, so now we need to simplify this mess. Okay, so the scalar part, let's do it first. The scalar part, it looks like we have a sine theta over 2 cosine of half theta that part cancels out, n dot x, and here you got a plus cosine theta over 2 sine theta over 2 x dot with n. So that cancels out, which is nice. And now you have the second term, which we will use a triple product identity. So that's a minus sine squared theta over 2 n cross x n cross x, and then dot with n. But here, this vector triple product is 0. Is 0 because, as we mentioned yesterday, the vector triple product is the volume. Signed volume. Okay, that's not a good diagram, but basically you get the idea. So this is a volume. But here now you see if two vectors are the same or in the same direction in a scalar triple product, it immediately tells us the volume is 0. So the scalar part vanishes as needed. It's supposed to vanish because here a position in 3D is encoded as a pure quaternion. X prime should have a 0 scalar part, so that's nice, as expected. Vector part. Now let's do the vector part. Here, the vector part is what? The vector part you get here, you get plus sine squared half theta n dot x. So this already looks kind of similar to the Rodriguez formula. N dot x times n. So there's this part, and then plus you got the cosine squared theta over 2 times x, and then plus cosine half theta sine half theta. At a certain point we'll use the double angle formula probably, and then n cross x. Okay, just a straightforward expansion. And next up you got minus cosine theta over 2 sine theta over 2 x cross n. Here you're probably going to use the anti-symmetry property of the cross product. And lastly, it looks like you need a vector triple product formula, which we thankfully derived yesterday. Sine square root of 2. Actually, you need a minus sign here. Sine squared of theta over 2 times n cross x, and then cross n. So there you go. So see what we can combine. So first of all, notice you have minus n. Minus x cross n is just n cross x. The anti-symmetry I was saying. X cross n, taking minus sign, is just n cross x. So these two terms can be combined into, so you get a 2 times cosine half theta sine half theta n cross x, which is exactly sine. Is a double angle formula, sine theta n cross x. So we recognize this term in the Rodriguez formula. So that's good news. And we also need the vector triple product identity. So the vector triple product identity, remember, you have the ABC-CBA rule, right? So first of all, minus back of the cab rule. So you got minus n times minus n cross x, n cross n, which is n cross x. There you go. So let's recall the formula. A cross B cross C, where B and C are crossed together. So that's the ABC-CBA rule, which we the back of the cab rule. So that's B times A dot C C A dot B. So it's back and cap. So that's the formula we derived yesterday when we reviewed vector algebra in 3D. So here, let's just apply this formula. Hold on. Yeah, so here A plays the role A equals N, B equals N, so B equals N. Let me write that, B equals N. A equals N, A equals N dot with X. Okay, C is X. Okay, and minus X times A and B taking dot product, so it's N dot N. So together is N times N dot X minus, simply minus X, because N is a unit vector. So that's pretty good. So therefore, vector part now can be simplified to sine square sine square half theta N dot X times N, and then plus cosine square half theta X. And as I mentioned, these two terms already combined into a single sine theta N cross X, so that's cool. And the final term, the minus sign is already observed, so that's already absorbed, so that's sine square of half theta times N times N dot X minus sine square half theta X. All right, so it looks like we need to use double angle formula. So first of all, you get 2 sine square theta, sine square half theta N dot X times N. And then plus sine theta N cross X. And finally, cosine square theta minus sine square theta over 2 times X. Okay, so use trig identities. The first one is 1 minus cosine theta N dot X times N. Sine theta times N cross X. So that's done. And lastly, you get, this is it twice cosine theta X? There shouldn't be a twice. Actually, there's no. It's just the double angle formula for cosine. Just cosine theta times X. So that's the vector part. But this is exactly the Rodriguez formula. This is exactly Rodriguez. Okay. So yeah, there you go. So therefore, today we managed to derive Rodriguez formula in 3 forms. The original vector form, we just verified that. Did we actually? I think I messed up somewhere. This is the original Rodriguez. Here, I should be a 1 minus cosine. Yeah, this is 1 minus cosine. Yeah, that's correct. Sine. Yeah. So we get 3 different versions of Rodriguez formula. The matrix form, that's the second form. Okay, so let's put a red label here. So that's the first one. You write purely geometrically, and then you rewrote that into matrix form. And finally, you got the quaternion form. This is the third form. Okay, so that's the third form. So as far as computation is concerned, so we have already have a lot of tools. Okay, so that's nice. But we're going to rewrite this q, okay, in the exponential form, much like in a complex number. Much like in complex number. I wonder how many people are still watching, but it doesn't matter, as I said. It's already okay. 3 people watching. That's fine. That's totally fine. Okay. So I'm saying that I would like to write q in the form of a exponential. So just like in a complex exponential, so it looks nicer. Okay. So I'm going to introduce a notation. Once again, this is just a notation or motivated definition. We're going to define or the notation. Define the notation that e to the n half theta is cosine half theta plus u. It's because it kind of looks like an Euler's formula. Plus n, okay, n sine half theta. Define this notation so that the quaternion rotation formula now reads x prime is e to the n theta over 2 times x, the original quaternion, and then times e to the minus n theta over 2. Okay, n is the vector, by the way. So as I was saying, like not me saying, but Lockheed mentioned, so this is reminiscent to the complex number situation. We use the complex exponential to represent rotation. But why does this notation make sense? Why does this make sense? Why isn't this an arbitrary definition? Okay, let's investigate. So just to motivate this notation, we're going to consider once again the Taylor series. So remember how we derived how we obtained the Euler's formula. E to the I theta equals cosine of theta plus I sine of theta. So one way we did that is to use Taylor expansion. So e to the I theta as the sum of I theta to the n over n factorial from 0 to infinity, and use the fact that here we use the fact that I to the 2n is minus 1 to the n, and I to the 2n plus 1 is minus 1 to the n times I. Okay, n equals 0, 1, 2, and so on. So you can split the sum in half. You get k from 0 to infinity. You got I theta to the power of 2k over 2k factorial. And then plus the sum, k goes from 0 to infinity, I theta to the power of 2k plus 1 over 2k plus 1 factorial. Okay, and this is nothing but the sum of minus 1 to the n, minus 1 to the k, theta to the 2k over 2k factorial, k from 0 to infinity. And then plus I, the sum of minus 1 to the k, zeta to the 2k over 2k plus 1 factorial. So k equals 0 to infinity. All right, so that's how we obtain the Euler's formula. The first one is a cosine, and the last one is a sine. So you can see the identity for I plays a role. The identities for I plays a role here. So what can we say about, at least formally, okay, what can we say about this n here? Does it play the role of I? Let's figure out. Okay, so well, here the n is what? N is the n, right? So I was saying that if we consider identifying n as we could identifying n as the so-called purely imaginary quaternion. So it's 0 plus n1i plus n2j plus n3k. Okay, what is this? What is this squared? What is n squared? Remember, n has norm of 1. N has square norm of 1. Right? N has let's consider the unit vector n as a pure quaternion. Okay. But remember, what is the formula for the n's norm? Well, the n's norm is just hold on. I'm saying is, what is n squared? Sorry, not n norm. Let's try to calculate n squared. N squared, by definition, is 0n vector times 0n. Okay, and clearly that's just 0 squared minus n dot product with n itself. Okay, and 0 times n plus 0 times n plus 0 cross n, n cross n. So the vector part is completely 0. So you just get minus 1 and 0. And this is identified as the real number 0. Real number minus 1 is just identified as a real minus 1 because the imaginary part is just minus 1. So this tells us n squared is minus 1. So n squared is minus 1, therefore it plays the same role. You can use the same argument. You use the same argument and imagine you can expand this and you just let, now you consider n as a unit quaternion. Its square is just minus 1. So therefore the Euler's, the same derivation for the Euler's formula works. So that's why. So n just works like I. So the quaternion n works just like I. Okay, that's the idea. Okay, so I think we covered the main material. Basically, we have Rodriguez formula in 3 forms. So now let's take a look at some concrete example, in particular the quaternion version, right? Because this is the one that we're least familiar with. So we wanted to see when, if you pick the Q to be I, J, and K, and what happens. So these are some special cases. It's certainly worth checking them out. So special cases. We'll do those special cases and we'll call it a day. So the special cases are as follows. So let's imagine picking the Q, the imaginary, not the imaginary, but the unit quaternion Q. Let Q to be ij and k and see what happens. Okay, so this is Q. Special cases. Because the thing is, if we are given theta and n, you can obviously calculate Q. But what if Q is a given quaternion, right? Its meaning needs to be identified. So special cases Q equals ij and k. Let's see what happens. First of all, add a super obvious special case if let's say Q is just including 1. Okay, including 1. Okay, so x prime, the formula x prime, big X prime equals qx q inverse. Here you have this is your Q. So now we have these special cases where Q equals 1. Of course, x prime is just equals x. So it does nothing. And does that make sense? Does that make sense? Because let's check that. Because when Q equals 1, that just means cosine of theta over 2 is 1. Cosine of theta 2 equals 1. And that's real, right? So cosine equals 1, meaning theta equals 0. Sometimes there are ways of proving vector formula with div curve. Okay, interesting. I didn't know. Okay, I didn't know, because this is still very new to me. I'm not an expert in quaternion, not by any means. As you can probably see, I was still trying to derive the multiplication table. Right? So yeah, here. So if cosine of half theta equals 1, then sine must equal 0. And the sine of half theta must equal 0. Sine of half theta equals 0, that just means theta equals 0, so no rotation then. Half theta is 0, okay? Or, you know what, of course this is multiple valued. Let's just say this is the multiple of 2 pi k. This is a multiple of 2 pi k, so it does nothing. You see, it doesn't matter what axes you choose. If you just multiply by, if it doesn't matter what axis you do. What doesn't matter what n is. You pick an arbitrary axis and you rotate that by a multiple of 2 pi, you get the original point. This is very uninteresting, okay? But it's an important case to check. And now let's say Q equals I. Q equals I, what does that mean? Well, Q equals I, we can write it as a vector form. So it's a 0 and the vector which is just 1, 0, 0. Or you can write it as E1, right? So E1, that's, so it's, let's write it this way. It's 0 plus 1 times I, or 0, 1 times I plus 0 times j plus 0 times k. So it's the same as 0 E1, the unit vector along x1 axis. Hold on a second, that does nothing either, because half theta is, no, it's not doing nothing. My goodness, oh, I'm stupid. Sorry, that's 0 E1. That's 0 E1. So Let's multiply that just without looking at the meaning of Q first. Okay, let's just do the brute force multiplication. So x prime is what? X prime is 0 E1 times 0x. Okay, and then times the conjugate, which is 0 minus E1. And see what that does. Okay, so because everything here is pure quaternion, we have a formula for that. Okay, so that's just the pure quaternion. You got the dot product E1 minus E1 dot x dot with x, and then you have the cross product E1 cross x. 0 minus E1. Okay, we can actually, okay, let's simplify at the very end. Okay, so let's keep calculating. So this way, the result is, well, the first one you get a 0, and then you minus 0, minus get the E1 cross x1, E1 cross x dot with E1. So that should be 0. That should be scalar triple product of vectors in which two vectors are the same. So this must be 0. The scalar is 0 as expected, which is nice. Always nice when things work out. So and in the vector part, you get minus E1 dot the scalar minus E1 dot with x times minus E1. Okay, and then, well, E1 cross x times 0, that's nothing. And finally, the cross product term, which is minus E1 cross x, and then cross E1. Okay, so what happens here? So this is 0, and then you get, this is just we change it to, so this is E1, change the order, because this is a scalar, the order doesn't matter. E1 times E1 dot x. E1 dot E1x, and here is what? Here we need to use the back cab rule. Okay, so plus E1 cross E1 cross x. Use back cab rule. So that's 0 E1 dot x. Back cab rule. E1 with x dot with E1. And then minus x E1 dot E1. Vector triple product identity. Okay, so now what do we have here? This is 0, and this is 2E1. This is 2E1 E1 dot with x. And then minus x. This looks like a reflection. Think about that. So here, if you have E1, here, this is, let's say this is E1. E1 dot x, that's because E1 is a unit vector. E1 dot x, that's a scalar projection of x onto E1. So this is x. Hold on a second. 2E1. We're saying that this is E1 times. Did I make a mistake here? So here I want the, that's positive, right? 0. Cab rule. So E1 x dot E1 what happened with x times E1 dot E1 is that a reflection about, hang on, it should be a it just looked like a reflection about x1 x axis the x1 axis, right? I'm still struggling to see it. 2E1 times E1 dot x minus x. Hold on a second. Let me just search this up. I think this reminds me of the household reflection formula. Householder reflection formula. There we go. But that's it's the opposite sign as our thing, right? Yeah, as I was saying that, you know what? It's perhaps a good idea just to look at the coordinates, just to plug in the coordinates. This way, things is clear. Because I'm having a hard time trying to interpret this stuff. But basically, here you have two. Let's use those are used for solving general. The householder reflection is used for solving least square problems. It's used for solving least square problems, like, you know, it's numerically how we do Gram-Schmidt procedure, householder reflection. So in Gram-Schmidt procedure, householder reflection basically does the QR decomposition, which is useful for solving a least square problem, which is useful for linear models. But here, I mean, that's gone too far. I'm just trying to interpret this relation here. So this shouldn't be too difficult. So you get 0 plus So the vector here, so the vector is if you encode this as a vector, as a pure quaternion, then it's just I, right? 2I. This is just 2I, exactly. And then E1 dot with X, that's just X1. That's just X1. And then minus X, which is just minus X1I minus X2J minus X3K. So it's just X1I minus X2J and minus X3K. So let's draw the picture here. So this is a general point, X1, X2, X3. Remember, this is X1, and this is X2, and this is X3. X1, X2, X3 is changed in the following way. X1 gets reversed. So this is the original. And 2 and 3 are the same. What does that mean? So 2 and 3 are the same. X1 gets reversed. Sorry, no, that's nonsense. X1 stays the same and 2 and 3 gets reversed. So that's a 180-degree turn with respect to the x-axis. So now it's clear. So you see, this is the original, and now X3 and X2 sign gets flipped. X1 meanwhile stays constant. So that's the new vector here. That's a rotation. I don't know the detail, just remember, yeah, Householder transformation, because probably that stat book is talking about numerical methods for solving least square problem, because linear model most of the time is just about solving least square problem, and least square problem numerically is done using QR decomposition, and QR decomposition numerically is done using Householder transformation. So that's the connection here. So yeah, this is just a rotation of X. Rotation about the x-axis, about the x1 axis. About the x1 axis by 180 degrees. Let's think whether this makes sense. So on the other hand, here you have Q equals I, which is 0, as we said, 0 E1. Yes, you don't invert the matrix unless for very small scale problem. You don't invert the Gramian, because in the closed form solution for least square problem involves inverting a Gramian, which is not the best idea. Typically, the matrix can be very large, and it's not and it might not be numerically stable. So there you go. This is Q equals 0 E1. This means cosine half theta is 0. Sine half theta is 1. And the axis n is E1. Axis n is E1. So indeed, this is rotation about the x-axis. And the value of cosine and sine tells us half theta is half pi. So theta is pi. Boom. Correct. Okay. So that's pretty cool. So this also is now verified. And I think, okay, when when q equals j, this is rotation about the x2 axis. Once again, another by 180 degrees. Same reason as here. Q equals K, rotation about x3 axis by 180 degrees. Okay. So that's pretty cool. That's the rotation formula verified. Okay. And now, I mean, we still have some time because I want to do this for a full 4 hour. Hang on. Let me think about what else can we do here. We talked about the Euler's angle yesterday. So let's just keep that now. And coming back to the Euler's angle. There you go. We talked about the Euler's angle. So the problem is, let's say, given these Euler's angle, how do we calculate the rotation matrix? Because that's another way to parameterize rotation. Given the Euler's angle, find the rotation matrix. It won't be the same as the Rodriguez formula because there's no one single axis. But given what we learned, right, this should be a relatively straightforward task. I mean, the algebra might look ugly, but still, we should be able to nail this. So given the Euler's angles, the three Euler's angles, can we find the overall rotation matrix? So that's our goal here. The question is, given the Euler's angles, calculate the rotation matrix. The overall rotation matrix, which of course should depend on the three angles. Okay, so just call that rotation matrix R of phi, theta, and psi. So the Euler's angle parameterization is the composition of three intermediate rotations. The rotations are defined relative to the standard basis. Right, so let me just give it a name. So the original basis, let's just call it E bar. So this is E bar. And then after the first rotation, so you leave E bar 3. Okay, this is 1, 2, 3. Okay, so you leave E bar 3 intact, and the rotation after the first step is called E prime, and then the second step, you leave E prime 1. Right, once again, 1, 2, 3. To keep track of things, 1, 2, 3. E1 prime is the same, and you get E double prime. So this is 2, this is 3. Right, and finally, you get E. Finally, that's the final result. 3 stays the same, and 1 and 2 are now in this configuration. Okay, there's some angle, there's a name for these angles. So phi is called, I think phi is called precession. Names. Phi is called precession. I don't know why, but yeah, that's the terminology at least. It's called precession. 然后sorry, I was speaking Chinese. Anyway, theta is nutation. It is nutation, and lastly, we got psi. Right? Okay, psi is spin. Psi is spin. So these are the names of these three Euler's angles. All right. Okay, so remember, there is a fact that we know from linear algebra. So the idea is we wish to express we wish to express the E R, okay, the R here. So R theta psi. Okay, this is, you should have three columns. The three columns are in E1, E2, E3. So in the final configuration, what happens? We just need the vectors E1, E2, E3. That's it. That'll be it. Remember, like in the 2D case, we remarked that the columns of the rotation matrix are the results of what happened to the basis vector. 2D rotation matrix is cosine theta, minus sine theta, sine theta, cosine theta. The first column is what happened to E1 after the rotation. The second column is what happened to E2 after the rotation. So we wish to do the same here. So can we figure out a way to express that? Well, so let's calculate the intermediate steps first, right? So that let's say E prime. What is E prime? E prime, we consider E prime as a matrix, okay? As a matrix, say E prime 1, E prime 2, E prime 3. This is a three-by-three matrix. And of course, this is obtained by rotating E1, E2, E3. So that's just, hold on a second. So E1, E2, E3 is, I forgot the matrix. I'm saying is E prime should be, let's just say this is our rotation matrix with respect to E bar 3, right? E bar 3 phi times E bar. Okay, and then similarly you get E double prime. What is E double prime? According to this description, oh, 3 here. Oh no, there's no 3. That's just, is E double prime is the result of R E bar, no, not bar, but just R E prime axis 1 by an angle of theta, and then times E prime. And finally, our E triple prime, oh, not triple prime, just E itself. E itself, the third rotation. The third rotation would be a rotation about E2, E double prime. Rotation about E double prime with angle phi. Angle psi times E double prime. Yeah, so now you need just to calculate the consecutive matrix multiplication. So there you go. Together, E is actually here you don't just, you can simplify notation. The first axis, rotation axis is just 3. Rotation axis is 3. And the second rotation axis is 1. No? Hold on a second. This is 3. Why you never rotate about 2? That's odd. So first you rotate about 3 and axis 3, and then you rotate about axis 1, and finally you rotate about axis 3 again. Appears that way, okay? So it looks a little bit weird, but this is how Euler's angles are defined. Okay, so according to this rule, then E is R1 phi times R, no, not R1 phi, R3 phi, R3 phi. R3 psi is the last step, and then times R2 theta, and then times R3 phi E bar. So it's just a matter of matrix multiplication now, and it is kind of, what is, oh no, not R2 theta, R1, my goodness, I'm silly. This is 1. This is 1, okay? And now you can use all the matrices derived in the first stream, in part 1. So the third R3 psi, that's cosine of psi, negative sine of psi, 0. Sine of psi, cosine of psi, 0, 0, 0, 1. There you go. And multiply that by the second one. Second one is rotation about 1, so it's 1, 0, 0, 0 cosine theta minus sine theta, 0 sine theta and cosine theta. Okay, and last one about axis 3. Axis 3 is what we already did that earlier. It's the same format, so you get cosine of phi, sine of phi, minus sine of phi, 0, sine of phi, cosine of phi, 0, 0, 0, 1. Okay, and then times E. So together, this is the rotation matrix for Euler's. This is a rotation matrix for the Euler's angle. That would be it. Okay, that's the answer here. Okay. Okay, I think that'll be it for today. We're gonna call it a day, and in an indeterminate future, I would like to revisit this stuff. I'd like to revisit it. Actually, you know what? Yeah, we're going to revisit this stuff and do an intro to Lie theory. Okay, using nothing but linear algebra. There's not going to be any topologies or differential geometry. Just we're going to see some important examples and statements in Lie theory, such as to be continued. Okay, to be continued. Baby Lie theory in the view of 3D rotation. That will be the exponential map. Exponential map that links the Lie algebra to Lie group. And also, we're going to look at the Hausdorff, Campbell, and Baker formula. Okay. Of course, these results, these notions and results have much deeper application compared than 3D rotation. But I think this will motivate the study of 3D rotation. Motivate the study of the general Lie theory. Okay, without any particular domain knowledge or deeper geometry and topology. Okay, that's it for today. Thank you very much, everyone, for joining the stream, and I'll see you guys next time. So tomorrow there will be the measure theory, which is usually on Tuesday, but last night I have other things to do. So tomorrow is going to be measure theory, and on Friday we'll do some information theory. Thank you very much for watching.